A real scalar field assigns a real number to every point in space-time. If the point P in a certain coordinate system has coordinates x mu of P, then the assignment is given by some function phi of x mu, which is just a real function. Suppose that we describe the same point P in a different coordinate system, x prime mu. Okay, I will not write this argument P anymore. Then the field phi will be described by another function, phi prime of x prime. But the value at the same point will be exactly the same. So phi prime of x prime is equal to phi of x, and this is the fundamental role of transformation of a scalar field. In fact, not only under Lorentz transformations or Poincare transformations, but under any kind of transformations if the field phi is a scalar under them. Okay, if this transformation is infinitesimal, so x prime of mu is equal to x mu plus some small transformation, whose form we will discuss later, and that for a moment we call epsilon mu, and that can be a function of the x's, not arbitrary but fixed for the moment. Then under this transformation you can study two kinds of transformations of the field. This total transformation, okay, which will be the total change phi prime x prime minus phi of x, and that for this scalar field is just 0 because of this transformation rule, or delta of phi without tilde, which is phi prime of x minus phi of x. This is similar to what we have done in mechanics. Now, there is also a similar relation between delta tilde and delta as in mechanics. If you expand phi prime of x, so let me write here delta tilde of phi as phi prime of x prime, which is x plus epsilon plus minus phi of x, and now you expand phi prime, then this is phi prime of x plus epsilon mu partial mu of phi prime minus phi. Now the relation between phi prime and phi is of first order in epsilon, and then this term would be of that difference would be of second order in epsilon, so we can just eliminate this prime and it would be the same, and phi prime of x minus phi of x is delta of phi plus epsilon mu partial mu phi. This is the general relation between delta tilde and phi. So knowing that this is 0 for the scalar field, we find that delta phi epsilon, so for this transformation at least, okay, is minus epsilon mu partial mu phi. This is the transport term, and it appears universally here. Okay, so here the transformation is just given by this transportation term. Now let's focus on Poincare transformations, infinitesimal Poincare transformations. These are given by these infinitesimal functions. So they are alpha mu, the translation, plus sigma mu nu x nu, where this is an infinitesimal antisymmetric matrix. It is antisymmetric with the two indices down. Now, bringing this into this infinitesimal transformation, we find that for infinitesimal translations, you have this transformation rule, and for infinitesimal Lorentz transformations, you have this different transformation rule. And these are the two transformation rules of a scalar field. The Lagrangian for the scalar field will contain not just the field phi but its derivative. So we want to know also how the derivatives of phi transform. Now observe that if phi is a scalar, partial mu phi really transforms as a one form just by using the chain rule. Okay, so let's do this explicitly. If we have in the prime coordinate system phi prime and the derivative is with respect to x prime mu, then this will be partial x nu partial x prime mu partial nu of phi, where now phi we have to replace here x by x of x prime. Okay, this is the transformation rule of one form, and now we can use it for these infinitesimal transformations. First, we want to compute this Jacobian matrix. Actually, the inverse Jacobian matrix depends on how you consider the transformation from x to x prime or x prime to x. We have to compute it for the infinitesimal transformations. So if the transformations are where x prime mu equal to x mu plus epsilon mu, we have to express now x mu, or here it will be x nu, as x prime nu minus epsilon nu, okay, of x prime. We can write x prime instead of x because again the difference between using x and x prime will be of order epsilon. We expand this in a series and the difference will be of second order in epsilon. Now we take the derivatives, partial derivatives x nu with respect to x prime mu, and the derivative of x prime nu with respect to x prime mu is just a delta. So this is one when they coincide and different when they are different, minus partial mu of epsilon nu. However, to first order, this is the same as if we just take derivatives. We write this as a function of x, and we take the derivative with respect to the x mu's, which I indicate like this, without any primes. Okay, so we find that partial mu phi, and let's write all these prime, it's equal to partial nu, so this delta mu nu minus partial mu epsilon nu, and then partial nu of phi, which is partial mu of phi minus partial mu epsilon nu partial mu of phi. Then by definition, delta tilde epsilon of partial mu of phi is given by minus partial mu epsilon nu partial mu of phi. Okay, and using this universal relation between delta tilde and delta, we know that delta epsilon of partial mu phi will be given by delta tilde epsilon minus epsilon mu. Now I have written just a different index instead of mu, that I used here. Here I used mu, but since mu is already taken, I am using epsilon nu, and this is the infinitesimal transformation rule for the derivative of phi. Now if we apply this general formula to the particular case in which epsilon represents an infinitesimal spacetime translation or an infinitesimal Lorentz rotation, we find that delta tilde epsilon, of alpha for spacetime translations of partial mu phi is 0, and delta tilde sigma of delta mu phi is minus sigma mu rho is minus sigma mu partial mu of phi. Okay, so if now we construct a Lagrangian that depends only on phi and the derivatives of phi, since the total variation of this Lagrangian under spacetime translations will always be 0. If it is only constructed for this with these building blocks with phi and delta mu phi, it is automatically invariant under spacetime translations, and under Lorentz transformations we find that, remember that this will be now the total variation under Lorentz rotations of phi, which is 0, plus and the variation under Lorentz transformations of partial mu phi. This we have, and this is equal to minus sigma mu partial mu phi, and okay, and if we wanted this to be 0, it is enough that this is proportional to partial phi mu phi. Actually, we don't need to do this calculation. The important thing is that we don't have to worry about the space-time translations, that we just need to build things which are automatically by construction invariant under any kind of transformations, like for instance with the mu phi. So with the mu phi we can construct the mu phi, which would be eta mu nu d nu phi, and then we know that the contraction of one form and a vector always gives an invariant. Okay. So this will be automatically invariant. You can express it like this if you want. And if you want to check that this formula gives 0, just for curiosity, then and this is your expression, so we take the derivative of what we write as d phi squared with respect to the mu phi, and this is clearly 2 times the mu phi. Now you go up here and you find that this would be, for this peculiar case, well, not peculiar, particular, sigma mu, a factor of 2, and then partial mu phi. If we raise this index and we lower this index, we find something antisymmetric, contracted with something which is obviously symmetric in mu and nu, because I can always interchange these two derivatives. So this is symmetric, this is antisymmetric, and as we explained before, this gives automatically 0. Oh, okay, it is obviously enough to construct things which are invariant by contracting indices like this. And the other possibility is to construct invariants which are just functions of the field phi, because delta tilde of phi is 0. Okay, so now with these elements we can try to construct an action for scalar field, and the only apart from Poincare invariance, what we are going to demand is that it doesn't have more than two derivatives. Okay, so something like the mu phi could be the term with highest derivatives that you can have. Now, you cannot have a term with only one derivative, because that would have a free index mu, and this can never be invariant. So, okay, you could have your action, okay, will be d for x, and the basic term that we can include is this one, which is actually the kinetic term for a real scalar field. This is the basic. If we allow for higher derivatives, okay, we could have powers of this, okay, this raised to any power, or more terms like this, with d phi raised to some power. Another thing that we can have is that we could add a function like this over here. But you should be convinced that if I have the mu phi, the mu phi over f1/2, f1/2, okay, I have this squared, I can always find a phi of phi such that the mu phi is the phi with respect to this other phi, and then the mu phi under this is equal to f1/2 of phi. So this would be a reparametrization or a field redefinition in this case of phi, and you can always eliminate this term if this is the only term that you have. So for simplicity, we will just take this with no f of phi whatsoever. So let's remove this. This is something to comment upon, because in more complicated settings this kind of terms cannot be ignored. Okay, so it is important to know that they can be added there, and of course they can be added just to the Lagrangian, just an addition, not as a factor of the kinetic term, and then this would be a potential, so just a function of phi. This is the simplest action that one can construct, and while the first term represents the kinetic term, the normalization is conventional. Okay, the convention is that the term that contains time derivatives should appear like this, squared. Okay, it's similar to the x dot that one has in a particle action. Okay, and with our conventions in which eta 00 is plus, this is exactly what you get. And this term represents this would be, if there was no potential, this would be the action for a free scalar field. The term v of phi represents a self-interaction. Depending on the form of this v of phi, you can describe just a mass term for the field, because this would be without the potential, this would always be a massless scalar field. And if you add something like m squared phi squared, then this term, if the potential is like this is a mass term. We are going to see this in a little while. Higher order terms represent interactions of the field with itself. And okay, why can I have interactions here without breaking a Poincare invariance? Because this whole thing is Poincare invariant. Well, in this case, because the only entity that one has is this field, and this action takes into account everything. The only thing that can transfer momentum is the field to the field itself, and this action takes into account everything. Okay, if there is an interaction with an external field that has another field whose kinetic energy is not taken into account and so on, then we may break some kind of invariance. But here is just not possible, not necessary, and you have a Poincare invariant of a self-interacting scalar field. So let's move on and let's try to find the equations of motion. We can do two things. We can just apply the Euler-Lagrange equations that we found, or we can vary the action directly as an exercise. So let's do both things. So the Lagrangian L is this expression, and we need to compute the derivatives, the partial derivatives with respect to phi. This is just, okay, I denoted with a prime, a derivative of the potential, and the partial derivatives of the Lagrangian with respect to the partial derivatives of phi. Okay, there are two, they appear symmetrically, so there is a factor of 2, and what you have is partial mu of phi. If you want to do this calculation in a bit more detail, okay, let's take a step back. You have you want to take the derivative of eta alpha beta partial alpha phi partial beta phi. Okay, so there will be one term and another term, the derivative of the first and the derivative of the second. Let's do it more slowly. So I have eta alpha beta, which is constant. I'm taking the derivative. So the derivative of partial alpha, it will be 1 when alpha is equal to mu. So I have delta alpha mu, and this one I don't derive. And then I have partial alpha phi, and similarly I have delta beta mu. Now in the first term, when I multiply by eta, I get eta with alpha replaced by mu, beta partial beta phi, and the second term I get beta replaced by mu, so it is eta alpha mu partial alpha phi. Then I take into account the symmetry of eta, so I can interchange these two indices, but also I can relabel alpha and call it beta or whatever. In any case, I can use eta to raise this index, and then I get partial mu of phi plus partial mu of phi, so I get 2 times partial mu of phi. Then taking into account the factor 1/2 that I have at the beginning, they have ignored. Okay, this 1/2, and then it's just partial mu phi. Then the questions are minus partial mu, partial L, partial mu phi, and this is just minus v prime minus partial mu phi. Okay, this operator, which is d0 squared minus di is the Laplacian, and usually we write it as a box. So this is minus box phi plus v prime and equal to 0, and this is the equation. Now we can investigate if there are any conserved quantities associated to the invariances of this action. We have proven the first Noether theorem only in the context of mechanics, non-relativistic and relativistic, but as you can suspect, there is a version for field theory. Before we study this version, we will consider one of the symmetries of this action, one which we haven't still mentioned, and which is the invariance under transformations that shift the value of the field phi. So phi prime is equal to phi plus some constant. The infinitesimal form of this transformation we can write as d phi equal to alpha. Again, now we call this transformation alpha. And it is obvious that the action is invariant under these transformations because, well, the action of the free scalar field, okay, without, so this means that V is 0 because only partial derivatives of phi occur in the action, and the partial derivatives of phi are invariant under the addition of a constant to the scalar field. So let's see now the implications. As usual, we vary this action in a different way using the same derivation we used for the equations of motion. These are transformations that do not act on the coordinates. And then we get exactly the same expression we got when we derived the equations of motion. So here you have the equations of motion. Now you have these particular variations and the total derivative, which had this form, delta phi, but now we apply it to these particular transformations. This is exactly what we did when we derived the equations of motion, but in that case, first we used the Gauss theorem to integrate, to obtain replace the volume integral by a surface integral, and then we used the boundary conditions on delta phi to cancel this term. We cannot do this anymore because obviously if these delta alpha phi's are constants, they are never 0 in any place in space-time. So we could never do that. That is not our purpose either, so that's fine. Anyway, what we find is this identity, and now this identity formally, because the boundary or the volume of integration play no role in this derivation. Since this is true for any volume, clearly this is an identity for the integrand, so this integrand must vanish. And we can express it in this way. Let's see, partial L, partial mu phi, delta alpha phi, then it's equal to minus the equations of motion times delta alpha phi. For this simple variation, delta alpha phi is a constant alpha that comes out of the equation, so of the derivatives in fact, and we can take as a common factor. And if this is satisfied for every value of alpha, then this is satisfied when we remove alpha and we get this identity. This means that if we call this derivative j mu, here we call it alpha because it is associated to the symmetries delta alpha here, then we find that d mu of j mu alpha, so the divergence of this object, which is called a current, vanishes on shell. Okay, now this smells to Noether theorem, but this doesn't look exactly like the derivative with respect to time of a conserved quantity. However, this is the form of the result of the first Noether theorem. How can we relate this statement with the conservation of something? Okay, we are going to see that indeed, when you have when this law is satisfied, then you have a conserved quantity, a conserved charge. So usually, when you have this expression here, you already say that you have a conservation law. Okay, now we are going to explain why this conservation law, this divergence equal to 0, implies that there is a conserved charge. So we are going to consider a particular volume V4, which will be the product of a three-dimensional spatial volume V3 and an interval between two instants of time, so it's the x00 and x01. This particular V4 can be visualized in this way. You have V3, which is always the same, its geometry doesn't change, it's some three-dimensional volume that evolves in time. And then if you start at the initial time x00, you end up at a later time x10. You also have V3 here, and this is the four volume swept by V3 when it moves in when it evolves in time is V4. Now we can see the consequences of having this conservation law, a conserved current, if we integrate this equation in this four volume. Okay, the first thing that we do is to rewrite the integral as an integral over the interval and an integral over the three-dimensional volume, d3x, and the mu, j mu, this divergence can be written in components in this way. I, these are the spatial components, I alpha. This component is going to be the charge density, while these three components will be the flux density or the current density. Okay, the names are associated to the fact that when you integrate this J0 over a three-dimensional volume, you get the charge that is enclosed in that volume, and this Ji tells you the density of current when you integrate it over a two-dimensional surface that crosses that two-dimensional surface at a given time. If you remember your definitions in electromagnetism, they are identical to this. Okay. So now we decompose this integral as the sum of two integrals, and because this V3 is independent of time, okay, it's always the same V3 but evolving in time, we can this integral commutes with the derivative with respect to time, and we have x00, x0, x01, the x0 and the partial derivative with respect to x0 of the integral of v3 of d3x j0 alpha. Okay, this is going to be the charge, by definition, the charge enclosed in the volume v3 at a given time, because this j0 still depends or may depend on time. So you get q, by definition, q at x0. Then the second term, you have this integral again, this time integral, and the integral d3x di ji alpha over v3, you can, in this integral, you can use the three-dimensional Gauss theorem to rewrite it as a flux integral, as an integral over a two-dimensional surface, which is the boundary of V3. So this is the integral over this two-dimensional surface. This again is proportional to the vector normal to the two-dimensional surface. This two-dimensional surface is nothing but the boundary of V3, and the integral is the integral of this ji alpha. So this is a flux of this charge across this surface at a given time x0, because it can also change with time. Okay, now we arrive to this expression. The first integral over time is this, but now this partial derivative here is becomes a total derivative because it acts on something that only depends on time. So let's write it like this, on q of x0, and the second term is an integral over time of the flux across the surface. Okay, this is the first term. The first integral is very easy to do, so it is q in x01 minus q at x00 plus the integral of this flux. Okay, and if you call this delta of q the variation of charge in contained in the volume, in the three-dimensional volume v3, between the initial time x0 and the final time x1, what you get is that this variation is equal to minus the integral of the flux. This is the general form of the conservation of a charge. It's not that the charge doesn't change, the charge contained in some volume, is that its change is related to the amount of charge that crosses the surface. So if there is as much charge as there was at the beginning, plus the charge that has entered as a flux of charge and has come out as a flux of charge. If V3 is infinite and it extends in a whole or the whole space, three-dimensional space, then the boundary is 0, and this integral will be 0. There will be no flux, unless, as it is usually said, that there are sources or sinks of this field phi at infinity. If that's not the case, then nothing crosses the boundary at infinity, and f of x0 is 0, and the variation of the charge contained in the three-dimensional volume, which is the total space, is conserved. It is always the same. So although this is just a basic example, you can consider this as a first explanation of the simplest version of the first Noether theorem in field theory. If you have an invariance of the action under some transformations of the fields, okay, which you have the parameters and the parameter independent transformations, you are going to arrive to the conservation law delta A of phi. This will be equal to minus the equations of motion delta A of phi, and this is true for any kind of fields. If these fields have indices, there will be a contraction over all the indices repeated in these fields phi and so on, and this will be the current which will be conserved. This is called the Noether current. And partial mu j mu a equals 0 on shell is the expression of the first Noether theorem. Okay, as we did in the case of mechanics, the first generalization is what happens if the action is not exactly invariant. So this is not zero, but it is the integral of a total derivative. And now total derivatives have this form. Okay, so it will depend on the particular transformations alpha that we consider. And if you go again through all the procedure, you will get the conservation of partial L partial mu phi delta A phi minus B A, because this B mu alpha will be linear in these parameters and can be written like this. Okay, and this with index mu. You need an index mu, and this will be again so the Noether current has an additional term